in astrophysics. So we start with, just 1 minute. So we have Enda Farrell from Nicolaus Copernicus Institute. So he's going to talk about training a machine learning classifier to predict Quasar Photometric Redshifts. So, and I think you have 25 minutes, I believe. Yes.
That's great, thank you.
So you can start now, yes. Thank you.
That's great. Good afternoon, everybody. My name is Enda Farrell, and I'm just going to take a whirlwind tour really over some machine learning methods that are used in astronomy at the moment. Just before I start, I just want to mention that there's actually some builders and workmen in my apartment building. So if you hear sudden drills or building noises, that's actually what's happening. So very quickly, I'll cover. Yes.
And excuse me, are you sharing your screen with us now?
Oh, so I have it shared on my screen, but is it
yes.
actually appearing?
Yeah, because we just see black screen now, so you might need to share your screen so we can see your slides.
Yes, I'll just.
No, it's okay. It happened to me yesterday. I was
yes.
warned after the second slide. So. Okay, yeah, we can see you. Yeah, we can see it now. You might need to put it in like a maybe full screen, please.
Yes, I have a feeling probably when I switch to full screen, does it actually disappear? Or
okay. So
yes.
Okay, maybe we can. Yeah, maybe you could manage to. Okay.
Yes, actually, I just realized it just may be a problem actually with this display driver.
Okay.
So I'll just try and do it this way. So really, there's going to be 5 main areas that I'll just go through in this talk. Really, at the moment in astronomy, we're in the age of big data. We've got a lot of all-sky surveys. They're coming in with terabytes of data. So really, the question is, how do we use all this data? One key aspect of the data is actually measuring the distance to the various objects. And this is where we'll talk about the so-called photo redshift measurement. Then we'll just quickly introduce a machine learning method, decision trees. It's often used to calculate photo redshifts. And then we look at deep learning, which is a kind of a more advanced method, which is again in a lot of talk these days. And finally, there's several off-the-shelf software packages that actually allow somebody quite quickly to get into this field because there's actually tons of data available and there's a quite low barrier to actually get in and start looking at the data. So, as I said, at the moment, we're in the era of big data. Just to give 3 examples, we've got the Dark Energy Survey. It's got a target list of over 400 million objects. It's wide-band photometric measurements it's making. Even on a higher level, you've got the LSST. It's literally tracking billions of objects. And there's a proposed 30-meter telescope that's going to take in up to 90 terabytes per night. So these are literally astronomical amounts of data. You can see actually back in the early 2000s, the Sloan Digital Survey was one of the first. And actually at the time, 200 gig of data, that was considered big at the time. So you can just see the rise at the moment. It's incredible amounts of data coming in. Now, one thing that everyone is trying to extract from this data is literally distance. You could say it's one of the key challenges in astronomy. How far away are things? So just to take an example from one of the projects, we've got the LSST. It's trying to track galaxy evolution. It's trying to constrain dark matter and dark energy. So through its hundreds of millions of objects, really, it's got to measure the distance to everything that it's coming up with. So really, distance is one of the key factors we're looking at here. So we'll just start off here with just looking at a proxy for distance, which is redshift. So the gold standard, the standard way to work out the redshift of anything, how far away it is basically if you've got good quality spectroscopy and you pick out any noticeable features in the spectrum, you can track those features as they're redshifted into the distance. So the the flux that you're measuring is shifted back depending on how far away it is. So for example, in the rest frame, we've got an emission line at around 6,500 angstrom. If that same galaxy feature was pushed back into the distance, its corresponding flux would be pushed back. So really that's the gold standard. From that you can work out the redshift and how far away something is. There's one problem with spectroscopy and spec redshifts, and they're very expensive to collect. So the LSST team gave a nice example. It would take about 100 hours integration time to actually work out the spectrum of one single faint target down at a magnitude of around 25. So if they wanted to get a spectroscopy for their entire field, they kind of with tongue in cheek said that would take about 50,000 telescope years. So obviously that's never going to happen. So we've got a bit of a problem here that we just can't get enough spectroscopy on the targets we're interested in. So really, another common method to get around this problem is to try and measure redshift, basically just using a crude, basically a cruder version of spectroscopy. So you've got 5 photometric bands. I think these are the Sloan digital survey bands. So instead of getting the full emission and absorption features, you just have a rough coarse-grained amount of flux coming in integrated over the various bands. So we're going to try and use that to actually get a measure of redshift. So for example, here if you've got a galaxy at redshift 0, so right beside us, but as it's shifted back, you can see that the various features of the spectrum are getting shifted back into the different bands. So really that could be, it's more or less a poor man's spectroscopy there. Now, the advantages and disadvantages of the photo redshifts, it's a bit of the opposite to this spectroscopy. So it's quick and inexpensive. So you don't need your 100 hours integration time. But the problem is you've got a lot lower precision. So as you can see, for example, as features are being shifted back and redshifted, we're actually losing a lot of information there. We're not able to capture various emission lines and features. So when we get to the machine learning, that's actually going to cause us problems later on. So you're going to end up with some degeneracy. So the problem is kind of set up now for the machine learning. We've got all this broadband photometric data. Our problem is we don't know how far away any of the sources are. And if you've got 30 to 90 terabytes of data, how could you quickly do that? So we can just switch here just to a broad overview of one part of the machine learning landscape. And there's 2 broad splits in this. You've got supervised and unsupervised learning. And basically, in a nutshell, supervised learning is where you've got different objects in different categories. And first of all, you tell the algorithm what is what. You explain to it, just in this toy example, what are red dots, what are blue dots. You train it, and then you let it identify new data for you. The other is unsupervised learning. Basically, it's more or less where you let the computer at the data yourself, and it's more or less a form of clustering. Let the computer and the algorithms uncover patterns in the data that a human may not necessarily see. So for this small example, we're actually going to use supervised learning, and it's going to be a form of regression. So I'll just expand on that a little bit. Now, unfortunately, because I'm not able to expand the screen here in PowerPoint, which is a pity, but I'll still run through the animations anyway. So we're going to train our supervised learning. We've got a model. It's black. I suppose it's a little bit of a black box because often we don't exactly know what goes on inside the model. And we're going to feed the model 2 different things. We're going to feed it our broadband photometry, basically what we measured in the UG, RAZ bands. But as well as that, we're actually also going to give it the correct redshift. So we're actually going to give it the answer. So we're going to give it, just to use the terminology, we're actually going to give it the features of the data, but we're also going to label the data as well for the model. So we feed both of these in, and we're hopefully, I mean, and this is the decision tree example, it's going to be able to figure out for each set of photometric data, because it's been given the right answer, it's hopefully going to be able to find a pattern and match photo-Z to spectroscopy redshift. So then the key stage comes then. We've got our trained model. Now we feed it some brand new data. And this is where all your 30 terabytes come in now. The model has never seen this. We don't have any spectroscopy for it. We feed it into the trained model, and hopefully it should come out with a realistic prediction of the redshift and hence the distance. So that's the theory of it, really. So our result really is we've got all our photometric images, and now we actually have an estimated redshift and an estimated distance. So we seem to be in business. But a key question is, how accurate are these really? So what we can do, it's fairly standard for this sort of redshift work, is we plot the measured redshift or the good quality redshift along the x-axis, and basically the machine learning prediction along the y-axis. So if all the predictions were right, we'd actually just get a line straight up the middle because everything would match the spectroscopy. But you can see straight away, you've got a few what they call catastrophic outliers, where the algorithm has got it completely wrong. And just to take one example, the actual spectroscopy is saying we've got something at redshift 3, whereas the machine learning algorithm is putting the same thing at around redshift 1. So a question is really, how is it getting it so wrong sometimes? So we've got one problem that causes a lot of issues for the classifiers, and it's in any piece of spectroscopy, you may have sudden dips or sudden breaks. So one example is, for example, around 4,000 angstroms, you can get these Balmer breaks where basically you've got a lot of extinction, you've got higher energy photons are being wiped out, and you've got a sudden drop in the spectrum. And you should be able to pick that up with the photometry. But unfortunately or fortunately, you also have other similar breaks. For example, at higher energies, you've got a Lyman break, where suddenly, I think it's probably neutral hydrogen is actually absorbing a lot of these high energy photons. So the problem for the classifiers is, for example, at redshift 7, you've got an AGN at redshift 7, and you see a sudden drop when you compare the red filter to a bluer filter. What the classifier isn't fully sure is, are you looking at a Balmer break there, or are you looking at an object at redshift 2 and you've actually got a Lyman break? So that's actually what leads to the degeneracy. One other problem is on the predictions, it's just coming out with point estimates. It's not really given a probability density function. It's not really quantifying the uncertainties. So there was a nice piece of work in 2016 where one scientist, he got the correct redshift for one quasar. I think it was at redshift 2, but he also plotted the nearest 64 neighbors to that particular one, the nearest 64 neighbors in color space. And actually, when you do that, you can see that basically you're looking at a bimodal distribution. So you've actually got a lot of degeneracy going along here. And if the algorithm is just taking the mean, that's what it's using to classify, it's going to actually predict it at 1 when actually it's wrong on both accounts. So you've got problems with multimodal distributions. And the final thing, and it's probably one of the biggest thing with machine learning, is there's actually a lack of training data. So because we're relying on spectroscopy to give us the answers for the near redshifts, as you go out to redshift 2, 2.83, you actually have less and less spectroscopy to train the classifiers. So we've got a lot of data in here at the near redshifts. It gets a lot sparser as you go out. And again, once you start feeding in unknown data, the classifier just isn't able to correctly classify the data. So one thing, just to do a little bit of the terminology in machine learning, what would in statistics normally be referred to as underfitting or overfitting, often in machine learning, they would just call it high bias or high variance. So basically, if your model, in this case, a decision tree, doesn't go deep enough, it's not able to correctly model the data. However, if you've got a decision tree that's too complicated, basically you're fitting to the noise, and when it sees new data, it actually doesn't perform very well. It's actually overtrained. So there's one way to get around this. Again, my apologies, the animations are missing for this now, but I'll still be able to talk through. This is all your input data here. This is data that's very good. You have photometry, but you have the correct redshift as well. So what you do is you just split it into 3 different categories. You actually just train the model on about half of it. Then you're actually going to check your model, and then you're going to do a final test. So the way that works is you supply half your data to train it. And here the key parameter for decision trees would be tree depth. How deep does your tree go? And you can see as the tree gets deeper, your error rate starts to drop. So in theory, you could say at a tree depth of 16, all its predictions are correct. But then you add the validation data that it's never seen before, and then you vary the tree depth again. And an interesting thing happens at around a depth of 10. You can see that actually the new data, the predictions start to get worse again. And the reason for that is basically at any higher depths, the model is overtrained and it's actually not doing as well on the new data. So to sum up, when you've trained got your correct depth, you give it a final brand new test data that it's never seen, and you're hoping with all of that you're actually getting in the middle, that you're not highly biased and you don't have too much variance either. Just it's worth mentioning, just in this area, there's some very, very good packages. What's particularly good about them, Astro Machine Learning and scikits that people are probably aware of, is what's really good is access to the data. So for example, a few lines of code, you can download 500,000 galaxies straight away, nicely calibrated photometry, and get going. And it's actually 8 or 9 years ago since I did some of this, and it's just amazing how much is available now. Just the final section of the talk, moving away from supervised learning or unsupervised learning, we've got the neural networks, or the deep learning. Now these have really taken off in recent years, and I think maybe really what made the news is there's the popular game of Go, which it's slightly more flexible and fluid than chess, and one of the world masters, Lee Sedol, was beaten by a neural network in 2016. I think AlphaGo was the network. It bet him 4-1, which up to then people thought fair enough with chess. You could train machine learning to beat chess players, but that Go was too fluid. So really, how did Google and AlphaGo manage this? So just very quickly, one step backwards. A lot of the time in neural nets, it's quite similar to photometric redshifts. You've got some input. This, for example, is you're trying to classify what number was written. So you've got your input and you want to say which digit it is. And the way this works is with a single layer, you pass in the pixels, but you also give it the answer on the outside. And in here, with the training, it comes up with the correct configuration that no matter which digit you pass into it, with the correct weights and the correct activation, it's going to come out with the digit on the other side. So this middle layer here that's doing all the work and the heavy lifting, that's called the hidden layer, and we've got one of those. But really what's changed is neural nets have been around for ages, since the 80s, and actually in theory there's a theorem that you can actually model any function using a single layer neural net. But the game changer really was when people had the computational power to actually start putting in multiple hidden layers. And that's where you can really start to handle non-linearity. So that was the game changer there. And that's where the deep neural nets comes from, that you've got a lot of deep layers. It's just worth mentioning that the one thing that made this possible was actually a hardware change. So a bit like astronomy, where new detectors can change the field. What happened here is you had your traditional CPUs that were able to multiply matrices just as scalars. Then around the mid-2000s, NVIDIA's brought out graphics chips for a lot of games, and it was much more efficient at linear algebra and matrix multiplication. It was able to multiply rows of vectors together. And then in 2015-16, Google announced its tensor processing unit, which is incredibly efficient at matrix-matrix multiplication, which is what deep learning it depends on. So really, it's a combination of software changes and also hardware. And now a lot of these, you can actually start up a machine on a public cloud and you could start measuring redshifts. One key feature, where does this fit in with astronomy, is before, when we were training the decision tree, we had to choose the photometry, maybe choose the magnitudes or the variability. So it needed a human expert to know what to feed into the model. The difference with deep learning is you take your entire image, pixelate it, and submit the whole lot into the network. So really, it's a more hands-off approach. You're not letting the human get involved at all whatsoever in it, and it's up to the computer to come up with its own interpretation. You also supply the correct answer. I think maybe it's worth mentioning this is actually what surprised experts when it defeated Lee Sedol. Because the neural network was let go on its own, it actually come up with a totally different approach that human players hadn't really seen. So it was almost that it was accessing another parameter space. And actually since then, since 2016, it's actually changed the way some of the grandmasters play Go. So hopefully in astronomy, we can have something similar to that. There's a nice paper in 2018 where a neural net was used to predict photometric redshifts. And compared to 10 years earlier now, you can see there's a lot less noise, a lot less scatter, and it's definitely a huge improvement using these nets. It's also worth mentioning as well, though, there's another method called template fitting, where you have a library of hundreds of thousands of spectroscopy and you try and match it against photometry. So this approach also used some templates as well. So just to finish up, just to say, along with the Astro machine learning, there's also a few off-the-shelf software packages with artificial intelligence as well. They've been used in the business world. They've been used in weather forecasting, biology. For example, a few lines of code will classify any image into 37 different categories of PET. The writers of this library actually bet Google in 2017. They bet their state-of-the-art algorithm just with a few lines of code. So it's a tremendous amount of power there, pre-packaged and ready to go. So to finish up, really, the conclusions are there's a data deluge, I suppose there always has been in astronomy. There's a huge amount of all-sky surveys coming up, but a lot of those surveys are only going to have photometric measurements. Somehow the predicted photo Z's have to be automated somehow, because no human will ever go through it. The problem is photo Z's have a lot of problems with degeneracy and not enough training samples. So there's definitely more scope for neural networks to offer an improvement of that. And actually there's a quite low barrier of entry as well to get into the field. And my final slide is, this regression and classification is actually really, really important in astronomy. And I suppose over 100 years ago, I suppose you had the absolute master classifier, 350,000 spectra, Annie Jump Cannon. And really you could say that she laid the groundwork for the later HR diagrams and stuff. So really it's just the importance of being able to make sense of the amount of data on offer. Thanks very much.
Okay, thank you very much, Enda, for this very interesting talk. So now we have some space for questions. If anyone, just raise your hand, please.
Can I have a question? Do you hear me?
Yeah, sure.
Yeah, thank you for this interesting talk, mostly containing a lot of general knowledge about machine learning. I omitted somehow what was the input data for your training set? Did you consider images or it was power spectra? Because I was kind of confused in this.
Yes, so it was actually just colors. So basically, normally just five colors. So rather than the actual raw flux measurements itself, just go back to it. So basically, your colors is subtracting one band from another. So it just gives you a measure of the difference between adjacent bands, and that can also give you a good mimic of the spectral features. But the thing is, that's what was used in this example in this decision tree. But there are other variables that you could pass in, not necessarily just colors. So oftentimes the colors, I think, are supplied as magnitudes, but you could actually just supply the actual flux measurements itself.
So basically, you took a picture, some image, and you extracted colors and put it to the training set vector, yeah?
That's it, yes.
And assign it to the known feature of redshift.
Exactly, for good quality measured redshifts, yes.
Yeah, so just complements the question. So did you, as you may agree, in machine learning, the even bigger field than important feature than algorithm is the pre-processing. So yeah, so exact pre-processing, or how did you extract it? So, or is it known field what you done, or is something new? Like, I mean, this extraction of colors.
No, this is quite standard, and actually this is one of the nice things about this field. All this data is actually pre-calibrated. Not all the photometry is on the same level, and it comes literally from the Sloan database, and that's actually what's so nice about it. It's literally SQL. It's just a database extraction language, and you can pull it down in a few minutes. So I suppose to answer your question, yeah, there was no pre-processing done on it. And that would be quite standard, and it is a dark art trying to clean and pre-process the data. That is tricky.
Okay, thank you.
Thank you, Radim. So, is there any other questions from the participants? Okay. It seems that we don't have any more questions. So thank you very much, Enda, again, so for your talk.
Thank you.